Okay, I'll go ahead and get started. We're continuing the story of light. Remember that light emerged as a phenomenon from our understanding of charge and the electrical magnetic fields created by charge, and light is a bundle of those electric and magnetic fields. And light has all these kind of interesting and glorious properties. We've talked about reflection, we talked about refraction, we've talked about interference. Today we're going to talk about diffraction. So the whole class is about diffraction. I'm going to explain what diffraction is, obviously, and we're going to talk about some examples of diffraction, some illustrations of diffraction. Specifically, say something about the nature of diffraction. Diffraction occurs for waves, so it occurs for light waves, but it also occurs for water waves and other types of waves. We'll talk about that. We'll talk about an example of diffraction which is called single slit diffraction. It's diffraction by a single slit, obviously. We'll look at that, we'll explore that, and we'll see equations, formulas describing that, and we'll look at some example problems involving single slit diffraction. Then we'll turn to what's called multi-slit diffraction. That involves multiple slits, obviously, and we'll talk there about the effect of multi-slit diffraction. We'll see equations that describe multi-slit diffraction, and we'll look at some example problems involving multi-slit diffraction. So that's the plan. But I better start with what is diffraction. We might know what diffraction is, or we might not know what diffraction is. And to start exploring what diffraction is, I just want to start with this illustration, which shows particles striking, impeding on a aperture or a slit in an obstacle. And it shows waves also impeding on a aperture or a slit in an obstacle. And it shows the differences between what happens when particles impede on a slit or an obstacle and what happens when waves impede on that slit or that obstacle. So on the left-hand side, that's the particles, and on the right-hand side, that's the waves over here. So here are the particles. As an illustration, I'm picturing them impeding on the two slits that we met in the last class. That was one of our examples in the last class. So here come the particles from the left, striking the obstacle with two slits, and we're going to see what happens. And then over here on the right-hand side, this is the illustration of the waves striking the obstacle with the two slits from the last class, and we're seeing the waves emerge from the two slits. When I picture the particles, what are particles? Particles are little discrete objects with energy and momentum, and so I pictured a bunch of little particles in red here streaming from the left towards the right and striking the obstacle. And then when I picture the waves are kind of diffuse, spread out objects that correspond to a flow of energy and momentum. When I pictured the waves, I pictured wave fronts. These are wave fronts. These are the crests of the wave that are traveling from the left to right. And so that's how I'm picturing the particles and the waves. When the particles strike the barrier, well, the ones that actually physically strike the barrier don't go through the barrier, they're just stopped by the barrier. The ones that miss the barrier go through the slits or the holes in the barrier, the apertures in the barrier, they just travel straight through. And so if we were looking at particles striking the barrier, then here comes the particles streaming in from the left, and then a thin pencil-like beam of particles emerges from the two holes on the right-hand side. So that's what particles striking our two slits looks like. It's different for the waves striking the two slits. Here come the waves striking the two slits from the left and from the left towards the right. Some of the wavefronts are striking and stopped by the material of the barrier. Some of the waves pass through the barrier, and when they pass through the barrier, the important, interesting thing is that they just don't emerge as a pencil beam of waves towards the right. Rather, they spread out from the apertures or the holes or the slits here. So you see these sort of spherical or curved or circular wavefronts that are emerging from the slits. So that's a big difference between particles striking a barrier when the ones that pass through the holes or the apertures in the barrier just pass straight through, they don't bend. And waves, which when they strike the barrier, the portions that pass through do bend as they emerge from the aperture. And that bending that occurs for waves but doesn't occur for particles is what we call diffraction. So diffraction just means that these waves are bent after passing through these apertures. These particles don't diffract, they're not bent as they pass through those apertures. And that's just what we mean by the word diffraction. That's all that the word diffraction means, is the bending of waves through apertures or around obstacles. Those waves might be light waves. We've been mostly talking about light waves, but they could be other types of waves, water waves, they could be sound waves, they could be gravity waves, all sorts of waves. Oh, here's a photograph of diffraction, so that we can see that it's a real thing. This is diffraction of water waves by an obstacle or through an aperture. And so if you look at this picture, this is some Californian beach here. Here is the beach, here's the ocean, and look at these obstacles or barriers in the ocean here. So actually it's a series of barriers and slits between barriers. And if you look at the region, look at the ocean, look at the region between the slits in the photograph, you see little circular wavefronts emerging. So these circular wavefronts, these sort of spherical wavefronts, are the diffraction of the ocean waves as they pass through the barrier. So here you're really seeing the diffraction of the water waves as they emerge through this barrier. They're also emerging through a barrier downstairs. Here you can see the spherical or circular wavelets as they emerge through that barrier there. So that's a real effect of diffraction of water waves. It's important and interesting that the effect occurs when the wavelength of the water waves, or any waves, is the same sort of scale, dimension, as the barrier or the aperture. And that's true in this case. Look at the distance between water waves on the screen. Look at the distance between the edges of the barrier. They're similar scale. And so that's when you get diffraction. Here's another picture. I don't know if you've been to a British beach, but here's a typical British beach. It's not quite like the US beach. Firstly, it's freezing cold. Secondly, there's no sunlight. Thirdly, there's no sand. This is actually mud. And fourthly, Fortunately, there's nobody on the beach, except normally there's some crazy person over here on the beach. And so this is a British beach, but also it shows a diffraction of water waves as they pass through an aperture. So here are the water waves coming in from the top right hand of this picture. They pass through this little aperture in this barrier, and those water waves will be diffracted, and you see these circular wavelets, the spherical wavelets of the water waves emerging through that aperture. So that's a second example of diffraction. Here's an explanation of diffraction. So here's an explanation of why it is that circular wavefronts, circular wavelets emerge from the aperture or the slit or the hole in a barrier. Why does that happen? So this is an understanding of why that happens, and I just want to walk through this. So in this sketch, which could be applied to the last two pictures of the water waves striking the barriers, or any types of waves, light waves, other types of waves. In this sketch, we've got the plane waves heading from the bottom of the sketch towards the top of the slide. So there's wavefronts heading upwards here. And midway on the slide, horizontally here, they're going to strike a barrier. So they're going to strike this barrier. There's material over here on the left in grey. There's material over here on the right. And so they strike this barrier, and some of the wave will impact the barrier, and some of the wave will pass through the barrier. And so we're seeing the effect of diffraction. The way we understand diffraction is that every point on a wavefront. So let's imagine the waves are rolling in to this barrier. They keep rolling in, and imagine we're focusing on one of those wavefronts. We're standing on one of those wavefronts, and it reaches the barrier. So here it is in magenta here. The principle for understanding the diffraction is that every point on that wavefront is a source of new waves, of what we call little wavelets, circular wavelets, spherical wavelets. And so I'm not drawing every point on this wavefront. I've just drawn 6 points on this wavefront. But there's many points on this wavefront. There's actually an infinite number of points on this wavefront. And they're also sources of circular wavelets or spherical wavelets of new waves, propagating waves. And so, for example, on this point, you see a spherical wavelet emerging from that point. I've drawn a bunch of crests, 4 of them, emerging from that point here. This point over here on the right-hand side, again, I've drawn a bunch of spherical wavelets that are emerging from that point. And for each of these points, I've drawn these wavefronts. Now, if you imagine these all interfering and combining destructively and constructively, what you see develop is a curved wavefront upstairs here from the superposition of all the little wavelets, another curved wavefront here, from the superposition of all the wavefronts, another one here. And so you see emerging through the aperture, through the slit, or through the gap, you see a wave that's emerging through there that is kind of spreading out at the edges. It's bending at the edges as the wave travels not just straight vertically through here, but emerges out towards the left, emerges out towards the right. That's diffraction. That's what diffraction is. And this little picture is explaining the diffraction as the superposition, as the interference of all the little wavelets that emerge from all the little points that are within inside that slit or that aperture between the obstacles. So that's how we how we think about diffraction. As I say, it occurs for all types of waves. So we're going to look at it for light waves mainly today, but it occurs, we've seen pictures of it for water waves. That's another common case of diffraction. It also occurs for sound waves. Sound is another type of wave, and you get diffraction in that case. In the case of sound, the wavelengths are sort of scales of centimeters to meters, so you get diffraction when you have obstacles that are scales of centimeters to meters. And so sound is diffracted right through a door. For example, you can hear somebody in the other room through the door because of diffraction of the sound waves. So that's an example of diffraction. And other types of more exotic types of diffraction, of more exotic types of waves, are gravity waves. They've been in the news. Also, something we'll talk about later on, which is matter waves. They're going to be in our news later in the semester. Okay, as I said, diffraction occurs when the aperture or the slit or the obstacle is the same size scale as the wavelength of the waves that are approaching the slit or the aperture or the obstacle. So there's two dimensions that are involved in diffraction. There's the wavelength of your waves, and there's the size dimensions of the slit or the aperture or the obstacle. And if they're similar, then you get diffraction. So that's a key thing. Another key thing is, if we were to make this slit narrower, supposing you were to make that slit narrower, how would that affect the diffraction or the bending? It would actually make the diffraction and bending larger. If you were to make the slit wider, it would make the affected diffraction and the bending smaller. So the smaller the aperture, the bigger the diffraction. The larger the aperture, the smaller the diffraction. And so that's an important feature of diffraction. Basically, diffraction is waves getting into what would be a region of shadow if the waves were actually particles. So, the water waves getting out here, and the water waves getting out here on the left and right, they're getting into regions that would be shadows, would be completely dark if water was a stream of particles. But these waves are a stream of waves, and so they can bend into those shadow regions. That's what diffraction is. Okay. When those waves emerge through that slit or that aperture or that hole, all those little waves, which we're thinking of as lots of little wavelets superimposing together, they're all going to interfere with one another, just like we saw the interference in the two-slit experiment and the soap bubble phenomena. So these little wavelets that are produced in the region of the slit are going to all be interfering with one another, and in some regions you're going to get constructive interference, in other regions you're going to get destructive interference. You'll get a pattern of constructive and destructive interference, and you can get a fringe pattern where you see large amplitude waves or small amplitude waves. You see bright fringes or dark fringes, just like you got with the two-slit experiment. You see a fringe pattern just like that due to the diffraction by a single slit. So not only does a pair of slits, two-slit arrangement, make a fringe pattern, and we understood that as the constructive destructive interference of the light or the waves emerging from the two slits. A single slit, that even makes a diffraction pattern of bright and dark fringes, because the multiple interference of all the multiple wavelets that are emerging through that single slit. So it's a very similar effect, the fringe patterns for a single slit compared to a double slit. I want to look at that a little bit. This picture here is a fringe pattern. So it's an arrangement of bright and dark fringes that are produced by red light being shone onto a very thin slit, single slit. Shine that red light onto that single thin slit, The emerging light is diffracted. All the wavelets of emerging light are interfering constructively, destructively with one another, and it produces a fringe pattern where the bright fringes are the constructive interference, the dark fringes are the destructive interference. And so that's what this picture is. Okay. This slide is to motivate or understand an equation for the dark fringes that you see when you have light passing through a single slit. So the equation that we typically use for a single slit is an equation that predicts the location of the dark fringes, and there's a pattern. Just like with two slits, there's a pattern of dark fringes, and so we're going to write down a formula for that. But I want to show you exactly how a dark fringe emerges. And on this slide, I'm showing you how the first what we call the first dark fringe, emerges when you've got a single slit diffraction pattern. So when light passes through a single slit, in the center of the light that passes through the single slit, say in the center of a screen that you're looking at the light passing through a single slit, is a bright fringe. So right at the center is a bright fringe, as you might imagine, right? There's a hole you've just passed through. There's going to be a bright fringe at the center. As you walk away from the center, say to the left or right, you'll walk into a region where it's dark. As you walk to the left, you walk into a region where it's dark as you walk towards the right. You know, this is light going through a hole, but you're getting a region of darkness. That's kind of weird, but it's not weird because it's destructive interference of all these little wavelets occurring at that place. So you get a region of a dark to the left and right of the bright fringe. That's the first dark fringe. If you continued walking right towards the left, or continue walking towards the right, you'd meet later on. You meet another dark fringe. That would be the second dark fringe. If you continue walking further, you meet the third dark fringe, the fourth dark fringe, and so on and so forth. So there's a whole sequence of dark fringes. This is a picture of how the first dark fringe emerges. And in this picture, I've got light rays that are heading in from the left-hand side. They're striking a barrier here. So this is material upstairs here. This is material downstairs here. This is the gap. This is the slit. This is the aperture here where the light passes through. We said that when the light passes through, every little point in this gap is kind of a source of these little spherical or circular wavelets that are going to interfere with one another. And I've just drawn a few rays that correspond to these wavelets, but I've drawn a very special circumstance. I've drawn a very special angle at which I'm looking at this slit. I'm looking at an angle where the light that comes from the bottom edge of the slit, so that's this light ray here. The light that comes from this bottom edge and heads towards my eye actually travels one extra wavelength than the light that travels from the top edge of the slit, then heads towards my eye. So that's the special condition that leads to the first dark fringe. The special condition that leads to the first dark fringe is that this distance is a little shorter from the nearer edge of the slit, the top edge of the slit in this case. This distance downstairs here is a little bit longer from the bottom edge of the slit, the further away edge of the slit in this case, and that difference in distance, what I call the path difference, is exactly one wavelength. And so that's when you get destructive interference, and it's because if this distance corresponds to one extra wavelength, when light from the top half of the strip is a trough, it means that the bottom half of the slit, the light from the bottom half of the slit, is a crest. And so they perfectly cancel one another out. And when light from the top of the slit is a crest, the light from the bottom is a trough. So again, it perfectly cancels out. So this is the arrangement where the interference of all the little wavelets emerging from all the little regions of this slit are perfectly conspiring to cancel one another and produce pure darkness. So it's a special case. This extra distance downstairs here, you can figure it out based on just a little bit of geometry. This little extra distance is the opposite side of a right-angled triangle, where the hypotenuse is the slit width. That's what I called A, that's the slit width. And the angle in the right angled triangle is the angle theta that we're observing the slit at. And so this is the opposite of that triangle. What's the opposite of a triangle with hypotenuse called A and an angle theta? It's A sine theta. So this distance is A sine theta, and all I'm saying is if that extra distance, A sine theta, is equal to a whole wavelength, you're going to get destructive interference. And so this is actually the master equation for the single slit experiment, that the first dark fringe appears when lambda equals A sine theta. It's as straightforward as that. It's just a bit of geometry and understanding this constructive destructive interference that's going on. Other slits, other dark fringes, like that was the first dark fringe. It's when this extra distance is lambda. Second dark fringe, when's the second dark fringe? It's when the extra distance is 2 lambdas. Third dark fringe, it's just when the extra distance is 3 lambdas. And so 2 lambdas corresponds to a different angle, a larger angle, because you've got to have a longer side for this triangle. 3 lambdas corresponds to a larger angle because you've got to have again, a longer length for this side to correspond to 3 wavelengths, and so on and so forth. This is a picture of the diffraction pattern due to light impinging this thin slit. So this is a picture of a single thin slit arrangement. We've got light that's striking the aperture, the slit from the left-hand side. We've got a diffraction pattern appearing on the right-hand side. The brown curve is the diffraction pattern. You see it's bright in the center. This means a large intensity of light. You see the first dark fringe upstairs here, marked at this angle theta. And there's another first bright fringe downstairs here. So these are the first bright fringes away from the maximum intensity in the center, the bright spot in the center, and these are their locations. Their angles are determined by that equation that we worked out. Remember, we said that A sine theta equals lambda when you get the first fringe. So if we wanted to calculate theta, sine theta will equal lambda over A, and that's all I've written down here. That the first bright fringe, dark fringe, I gave it the label 1 because it's the first one, is the sine of its angle is lambda over A. The other first bright fringe downstairs here, I gave it a label -1. It's the first dark fringe, but in the opposite direction from the other dark fringe, is at minus lambda over A. And so these are the equations for these dark fringes, and then the second dark fringe is upstairs here, downstairs here. That's when the sine of the angle is 2 lambda over A. And the third dark fringe, I didn't mark that, but that's when, so it's labeled with an integer 3, m equals 3, and that's when sine theta equals 3 lambda over A. And so those are the arrangements of dark fringes. I should say something here. This picture is misleading because it's absolutely not to scale. So it's absolutely not to scale. A, the slit width has to be tiny. If for example, if we're looking at light rays, it has to be a tiny, tiny slit, a very, very narrow slit. The distance to the screen, for example, if we're looking at light rays, is typically large. So A might be some tiny fraction of a millimeter. The distance to the screen might be meters. And so really, this is very, very small, and I've exaggerated it to make it too large. This is very, very large, and I probably shrunk it to make it smaller. So it's absolutely not to scale. Also, this angle is very small. It's not as large as I've drawn. That's misleading. On this second figure, it's the same figure again with the slit, the light approaching the slit, the screen in brown here, the diffraction patterned on the screen, the bright maximum at the center, the first minima above and below it, the second dark fringes above and below them. But I've labeled not the angles at which the dark fringes occur at. In this slide, I've labeled it with the positions on the screen as measured from the center, as measured from this 0 here. These equations, unlike the previous equations for the signs of the angles of the dark fringes are exact equations. These equations for the locations of the dark fringes on the screen in terms of the slit separation and the screen distance. These are approximate equations. They're based on the angle theta being very small, which is normally a very good approximation. So I've indicated that these are not actually exact. These are approximate by these funny approximate symbols here. Anyway, the position of the first bright fringes is just given by this little expression here. Just depends on the various dimensions of the setup and the wavelength of light. It's just the wavelength of light times the distance to the screen divided by the slit width. So it's lambda L over A. That's the location of the first dark fringes, and then for the second dark fringes, it's just 2 lambda L over A, because we needed twice as much path length for the second dark fringe. For the third dark fringe, it's not labeled on here, it's 3 lambda L over A, because you need 3 times as much path length for the destructive interference for the third dark fringe. And so these are equations that are often more useful because they're in the language of the slit separation and the screen distance. So summarizing all that, this is just a summary slide now. This is the master equation that describes the location of the dark fringes, the darkness, the destructive interference that occurs for a single slit. These dark fringes appear away from the bright spot in the center, and they appear at angles theta or positions y that are given by this equation here, where L in this equation is the wavelength of the waves that are impinging on the aperture of the slit. So lambda is the wavelength. M is the index of the dark fringe. So it's m equals 1 for the first dark fringe, m equals 2 for the second dark fringe, m equals 3 for the third dark fringe. A is the slit size, the slit width, the aperture width, and L is the distance from the aperture to the screen. It's the screen distance from the aperture. And so this is that master equation. Let me just show you a little video showing you single slit diffraction. In the video, I'll show you the fringe pattern from single slit diffraction, so we believe in it, right? Because it really is a remarkable effect. You pass light, so think about this, you pass light through a single slit, and on a screen behind the slit, you get a pattern of bright and dark fringes. I mean, that's an amazing thing, and it's telling you amazing things about the light. Anyway, we're going to see that happen with light, and what I'm going to do is actually we'll see it happen as I vary the width of the slit, as I vary the size of the aperture. So it's like I got a letterbox, and I'm going to change the height of the letterbox, and we're going to see how that affects the diffraction pattern. Oh, that's, don't want to show you that. Here we are. So here this is green light that has passed through a single slit and is now illuminating a screen. So this is light that's gone just through one slit. You've got, it's kind of obscured right now. Let's get rid of it. Stop this. You've got a bright fringe in the middle, a bright spot in the middle. That's the light that went directly through the center. You've got a dark region over here where the light is destructively interfered with itself, and you get darkness. And you get one over here. These are the m=1 dark fringes that we're predicting the location of as being lambda L over A. Then you get another bright spot over here on the left and right. And then you got the second dark region. This one here on the right, this one here on the left. That's predicted by us to be at a location on the screen that's 2 lambda, the extra distance, times L over the slit separation A. So that's the location of m=2. And then this one also shows that m=3 is here, m=3 is here. We've got m=4, and m=5, and m=6, and so on. And so we see a whole pattern of the diffraction pattern of the light emerging through just one single slit. It's really an amazing thing. And then I'm going to change the size of the slit. And we're going to watch this pattern go wider. What I'm actually doing is narrowing the slit. So the smaller you make the slit, now I'm going to make it wider again. The narrower you make the slit, the broader the diffraction pattern gets. And the wider that you make the slit, the wider you make it, the narrower the diffraction pattern gets. So let's just do this one more time. I like it. So this is making the slit narrower, and the pattern is stretching out. And it gets so large here, we just see the bright spot in the middle. And then I'm going to go the other way. I'm going to make the slit wider, and then the pattern shrinks down. And we see many more of the minima, the dark fringes. Okay. Let's look at an example calculation. As I mentioned, that diffraction is a feature of waves. It doesn't matter whether it's water waves or sound waves or light waves or gravity waves. They all exhibit diffraction. If your wavelength is of order of your aperture or your obstacle. This particular example involves microwaves striking a aperture. So, you know the microwave at home. It's just the waves that are inside that microwave. These microwaves are now going to strike a aperture that is a window. We're told the size of the window, the width of the window. So we're being told that variable A, that was the slit size, that the microwaves are going to strike this window. We now know that, we're told that the microwave's wavelength is 5 centimeters. The window size is 36 centimeters, so that we should be thinking about diffraction, because the wavelength of the microwave is 5 centimeters and the width of the window are similar scales. That's 36 centimeters. So we're going to get diffraction, which is the bending of the microwaves as they emerge through this slit and their interference. And we can watch the interference on this wall over here. And we're told that this wall is 6.5 meters away, and we're asked, where on this wall is the first dark fringe of microwaves, of these waves that we're calling microwaves, that come out of a microwave oven, for example. So we're going to find the location of it. And I've called it Y. That's typically what we call the location of the fringes. It's Y1 because it's the location of the first dark fringe. Okay. I'll do this on the camera. That don't look right. Okay. So we were told some information in that problem, some dimensions in that problem. It's all about, dimensions, basically. We were told the wavelength of the microwaves, 5 centimeters. We were told the size of the slit, the size of the aperture, that was 36 centimeters. We were told the distance to the screen, that was 6.5 centimeters. And we were told to think about the first dark fringe, which we label with the integer m equals 1. So that's all the information we're given. And I just wrote it down here. So lambda 5 centimeters, A slit width 36 centimeters, L screen distance 6.5 meters. There's 2 ways that we could solve this. One way we could solve it is by that equation relating the wavelength of the light to the location, the position, the Y value of the first fringe. So let's try it that way. So in that case, lambda, I should say, is approximately equal, because this does use a small angle approximation, would be equal to a Y1, that's the location of the first dark fringe, divided by L. So we're going to use this little equation. We're going to rearrange it because we know the wavelength. We know the slit separation. We know the distance to the screen. So we know lambda, A, and L. What we want is Y1, that location of the fringe. And so I'm going to rearrange it, which means I'm going to get an equation that is lambda L over A. And then I've just got to fill in the various values of the wavelength and the screen distance and the size of the window. And so I can plug those all in. I've got to be careful I do it all in the same units. I put it in meters. 0.05 meters is the wavelength of the microwaves. 6.5 meters is the distance to the screen. 36 centimeters, so that's 0.036 meters, is the width of the window. And if we do that calculation, we get 0.9 meters, 0.90 meters as the location of that first bright dark fringe on the wall. And so that's just one example of carrying out this calculation of the fringe pattern for a single slit, and understanding the fringe pattern for a single slit. I could have done this another way. So this is maybe method A. Method B. I could have said, well, look, this is an approximate equation. Maybe I should check this with the exact equation for the position of the slit based on first calculating the angle of the dark fringe. So the exact equation that I'm talking about is that the angle for the first dark fringe, so I'm going to call that theta 1. The angle of the first dark fringe is given by this little relationship here. It's the wavelength of the light equals a sine theta. And that was the first equation we met. So we could use this, and we could solve this. We could solve this for theta. So if I wanted to solve this for theta, I would divide through by a. So I get lambda over a. That would equal sine theta, and then I could take the inverse sine. So lambda, I know, I can plug it. I won't plug in the numbers this time. I could plug in the 5 centimeters. A I know is 36 centimeters. I can plug in the 36 centimeters. And then I could take the inverse sine, the arc sine of that, and I get an angle. It's 7.93 degrees. So that's the angle of the first dark fringe, and that was exact. That's not approximate. Once you got the angle of the dark fringe, we could calculate, crap. We could calculate the position of the dark fringe. Let's imagine this crappy triangle. Here's a triangle. Here's the angle that we just calculated, theta 1. Here's the distance to the screen. That's the adjacent to the angle. Here's the position on the screen. That's the opposite of the angle. Those three things are related, but the tan of the angle is equal to the opposite over adjacent. So we're going to just use that and write an equation that y1 equals L tan theta 1. We now know theta 1, it was 7.93 degrees. We know L, we were told it in the problem, 6.5 meters. And so if I just carry out this calculation, again I won't put in the numbers, I got 0.91 meters. And so our initial approximate calculation was pretty good. It was good to about a part in 100, that sort of scale, but it wasn't exact because it does rely on the angle being small. This angle was pretty small, 7.9 degrees for the microwave diffraction. Typically in a problem with light, the angles are very, very small, and this approximation tends to be very, very good. Anyway, I just wanted to show you that example. Quiz question. So let me publish this. This is about the diffraction pattern of a single slit and how that diffraction pattern changes when you change the slit size. So it's just a question about that. We are now 10:17. So this question asks us, to think about single slit diffraction pattern again. And it says that in a single slit diffraction pattern, we're going to change the slit width. We're going to increase the slit width. And so the question is, if you increase the slit width, how does the diffraction pattern change? So one possibility obviously is that it doesn't change at all as you change the slit width, although that might sound kind of unlikely, I think. The other possibilities are that it might stretch out or it might shrink down. So increasing the slit width, does the pattern stretch, i.e. the distance between fringes get larger? Does the pattern shrink, the distance between the fringes get smaller? So I'll give you another moment or two to think about that. So we looked at the video of exactly this. We looked at green light passing through a single slit. And we looked at the diffraction pattern of the green light from the single slit, and we looked at, in particular, at the dark fringes that surround the bright central spot. We saw that when we decrease the slit size, when we make it smaller, the diffraction pattern actually blows up, gets larger, expands. When you increase the slit width, make it larger, the diffraction pattern actually shrinks down, gets smaller, gets compressed. So the answer here is if we're going to make the slit large, we make the slit larger, we're increasing the slit width, we're going to decrease the distance between the fringes. The whole pattern gets smaller. The idea is that actually if you make it really large, if you make the slit size much larger than the size of the wavelength of the waves, then basically diffraction goes away. Diffraction's a issue or a phenomenon or an effect when the wavelength of the waves and the size of the obstacle, the size of the aperture, the slit, are of the same sort of scale. If we make the aperture much bigger than the waves, the diffraction effects basically vanish. Okay, there's one more example of diffraction in the slides with visible light rather than microwaves, electromagnetic radiation, but I won't go through that one. I want to go on to the last topic, which was multi-slit diffraction. So I want to talk about this. Just so that we don't get confused about symbols, and I've sort of made it confusing because I didn't fit all the text on the bottom. I'm trying to point with a clicker. In the single slit case, we describe the slit size with the variable A. So that's the width of the slit. In the multi-slit case, we're going to describe the slit separation, the distance between neighboring slits, adjacent slits, with the variable D. That'll be the slit separation. So we're using A for slit size in the single slit case. We're going to use D for slit separation in the multi-slit case. In the multi-slit case, you know, we really imagine that the slits are very thin compared to their separation. So that's kind of our picture, how we visualize the multi-slit case, that the slit size is negligible and it's only the slit separation D that counts. Whereas in single slit case, we're entirely thinking about the slit width. I don't know why this stopped working. Okay. This is a slide that basically walks us, takes us on a tour from single slit, which we've been just exploring, and we now understand the diffraction pattern of a single slit, towards multi-slit. It actually takes us from one slit to two slits to three slits to ultimately five slits. What we're going to be looking at in our examples and illustrations are way beyond this. We're actually going to be looking at cases where you can have thousands of slits. You can actually have tens of thousands of slits. So our numerical examples are going to be based on huge numbers of slits, thousands or tens of thousands of slits. But this shows you kind of the progression from a single slit to 2 slits to multiple slits. Gives you an idea of what's going to happen in the large number of slit case. Remember that we've just been looking at the single slit, but we also looked in the last class at the double slit. Here's a comparison of single slit. The first dark fringes are over here on the right. You can just see there's a little red spot here. I don't know if you can see it, but the first dark fringe is here, and there's a dark fringe over here on the left. There's a little red spot over here. This is the pattern for 2 slits. Remember, that was also bright and dark fringes, and we had an equation for those bright and dark fringes, but this is the 2 slit pattern. And then this is as you go to 3 slits, 4 slits, 5 slits. Now, lots of complicated things happen as you go to 3, 4, 5, and more slits. But I want to tell you about one overall thing that's happening, which is the key thing that happens when you've got hundreds, thousands, or tens of thousands of slits. The key thing is that the bright spots get more and more concentrated. So the widest bright spot in this picture is the single slit. That's a very wide bright spot. The 2 slit is narrower bright spots, but then if you look here, as you start walking down here, the bright spots are getting smaller, and the space in between them, maybe that's easier to say, is getting progressively larger. And if you walk to very large numbers of slits, and I'll show you that on the next slide, what you discover is that the bright spots become amazingly, remarkably sharp, really, really bright, sharp, bright spots. Between them are these vast regions of darkness, of no light. What you're doing as you go to many slits, hundreds, thousands, tens of thousands of slits, is you're making these really, really concentrated regions of constructive interference where every slit is interfering constructively. A super intense, a super bright, very sharp spot. And between them is these huge deserts of basically destructive interference. You've really concentrated all the intensity of the light, all the energy of the light into just a few bright spots with just darkness in between them. So let me show you that. And it's quite an amazing thing. Here is a diffraction pattern. Actually, there's 3 diffraction patterns with 3 different colors of light where we've got thousands of slits. Not 1 or 2 or 3 or 4 or 5 from the last slide, but now we've got thousands of slits. Here's the blue diffraction pattern up at the top here. Here's the green diffraction pattern in the center. Here's the red diffraction pattern at the bottom. Remember that blue has the shortest wavelength. Green has an intermediate wavelength between blue and red red has the longest wavelength. And you see here, right, that the blue has shorter separations, sort of destructive darkness between the bright spots. The red has larger separations between the bright spots, and the green with the intermediate wavelength has an intermediate separation between these bright spots. So this is what I'm meaning when I say, to me this is just amazing. These bright spots are really, really intense. All the light's energy, all the light's intensity is focused in these bright spots. And then between them, despite the fact you shone all this light through these slits, between them are these great big gaps of destructive interference where it's just dark. And so this is the pattern that emerges when you have hundreds or thousands or tens of thousands of slits rather than 1 or 2 as we've discussed, or 3, 4, and 5 as I showed. When you have hundreds or thousands or tens of thousands of slits, we use a different name for that arrangement of slits. We don't say it's a multi-slit arrangement with hundreds, 1,000 or 10,000 slits. We call it what's called a diffraction grating. So grating means a huge number of slits. And diffraction grating means you're going to look at the diffraction pattern from a huge number of slits. So these patterns are here, that you see here are made with a diffraction grating that has thousands of slits, which the light is passing through, and in particular spots interfering constructively, but in between is just these big deserts of destructive darkness. I can show you a video of this, I think. I think I'm going to show you a video. It's made of this light here. This is a special light that, it was on the whole time. I'm not meant to run that for more than a minute. Anyway, this light here, inside that light is mercury vapor. And you're seeing the light emitted by, if I spin it around, by mercury vapor. And it's this kind of sort of, relaxing blue light, like a blue sky. Take this light and shine it on a diffraction grating. That light shining on a diffraction grating will produce these bright spots of really intense light separated by these regions of darkness, destructive interference, and the locations of the bright spots are be determined by the wavelength of this light. Now what's really interesting is this mercury light it's not just some sort of bluish spectrum of light, but it's some very discrete, distinct colors that are unique to mercury. And so if we shine this light on a diffraction grating, we can expose kind of the fingerprint of mercury. It's light fingerprint, the specific colors in mercury. And mercury has a fingerprint, and every atom in the periodic table has its own particular fingerprint. And this is how we first started exploring atoms, by looking at their light fingerprints. And we're going to do this later on in the semester. But I just want to show you the diffraction pattern from that lamp. Here it is. It's not a very exciting video, but not much goes on. But with a diffraction grating, I'm shining that blue light on a diffraction grating, and I'm getting this pattern. That color light there that looks like a nice light blue is actually this blend of different colors. There's a strong violet line in there, and then it's sort of mixed in with some green and yellow, and this producing this colored light here. And so when we use diffraction gratings, it's a way of exposing these fingerprints that every atom has, which is going to be a key to understanding atoms and matter that we're going to meet later on in the course. So this bit is just a little bit of foreshadowing of what's going to happen later on in the semester. Okay, what am I doing? Nobody knows. This is the equation that describes the locations of those beautiful, intense, bright spots for a diffraction grating. So it's this simple equation here. The symbols in this equation are the symbols that we've met when we've talked about two-slit interference and single-slit interference. We've met all these symbols in those other examples. So lambda is the wavelength of the light that you're shining on the diffraction pattern again. So the whole thing is based on it it being waves that you're shining on the diffraction grating or the multi-slit arrangement, because that's going to produce the constructive destructive interference that produces the pattern of bright spots and dark regions. So lambda is the wavelength. M is again an integer that's labeling the fringes. The complicated thing about M to me sometimes is that depending on whether you're thinking about bright fringes or dark fringes, and whether you're thinking about single slit, two slit, or diffraction grating, the integer m's sometimes starts either at 1 or starts at 0. So we've just met a case where it started at 1. M equals 1 was the first dark fringe in the single slit pattern. Here, just to confuse things, M equals 0 is the first bright spot in the diffraction pattern. There's no way around this. It's not a convention, it's just nature. There's a bright spot in the middle, we label that at M equals 1. The first dark spots were away from the middle. Sorry, the bright spot in the middle is labeled M equals 0. The first dark spots in the single slit case was M equals 1. They were away from the center of the screen. Anyway, this integer starts at 1, but then it progresses, it starts at 0. Then it progresses in the same way. So we got 0, then plus or minus 1, then plus or minus 2, and plus or minus 3, and so on and so forth. D here is the slit separation, remember. That's what counts in the diffraction grating. It's the distance between the slits. It's not the slit width. That's what counts in the single slit arrangement. And then angle theta, again, same meaning of the angles. The angle away from 0 degrees straight towards the screen at which you're looking at the diffraction pattern, the pattern of bright and dark regions or bright and dark fringes or constructive and destructive interference. So this is the equation that describes this situation. Okay, here's an example, an illustration for us of diffraction from a diffraction grating, i.e. from something that has multiple slits, hundreds or thousands of slits. We're told in this particular problem the light that we're shining on the slit, so we're told we're shining light on the slit first of all, we're told it's red light that we're shining on the slit, we're told it has a wavelength that is 640 nanometers, that's the wavelength, that's a long wavelength for visible light, that's red light. We're shining it on a slit. This is typically the way that diffraction gratings are described. Diffraction gratings are normally described by how many lines they have per centimeter. That's how many slits they have per centimeter. This diffraction grating has 2,000 slits per centimeter, 2,000 lines per centimeter. So we're told that number. And so given that information, it's information about the diffraction grating itself and information about the light itself, we're asked to figure out what is the angle of the M equals 1, first order maximum of the red light. And there's a little picture there where we're imagining this, this is the diffraction grating with many slits, described by there being 2,000 of them per centimeter. And then this is a screen on which we're looking at those bright spots and dark regions, and we're asking the question, what is the angle, what is the position of that first bright spot away from the center? That's the M equals 1 bright spot. Okay, so let's see if we can calculate this. Maybe I'll do this on the document camera. That was the problem I skipped. This is the problem that we're going to do now. So I wrote down the information we were given. We were given the wavelength, 640 nanometers, and we were given the description of the diffraction grating, that there are 2,000 lines per centimeter. What we want in our equation is what we call D. It's the slit separation, and we're told that indirectly with the lines per centimeter rather than directly. We're told the number of slits in every centimeter, but we want the separation between a single adjacent pair of slits. So what's the relationship between these two things? Well, the relationship is that the separation between a pair of slits is 1 over the number of lines per centimeter. So if I put in here 2,000, it's 2,000 lines per centimeter. The units are per centimeter. 1 over that number comes out to be 5 times 10 to the minus, I'm going to put it in meters, 6 meters. So the units of this quantity in the denominator, denominator were inverse length. They were inverse centimeters. That means that the units of the slit separation will be centimeters when I take the, or meters when I take the inverse of that. So this was 5 times 10 to the minus 4 centimeters, and then I converted it into meters, so it's 5 times 10 to the minus 6 meters. So that's the first little bit of, that's kind of like the warm-up before the actual calculation. Now I want to figure out the angle at which this first bright spot, the m equals 1 bright spot, away from the central bright spot, the m equals 0 bright spot, occurs at. So the master equation was that, this is wrong, d sine theta equals m lambda. If I apply that master equation to the particular case of the m equals 1 bright fringe, I should have said I also know m equals 1, then it tells me that d sine theta 1, the angle of the m equals 1 bright spot, is equal to lambda. And I can just rearrange this then to find out what theta is. So if I want to find out what theta is, theta 1 is, I could divide through by d, so it'd be lambda over d. Sine theta would equal lambda over d. Let's take the arc sine, inverse sine. So theta 1 would be arc sine, inverse sine of the ratio of the wavelength of the light to the slit separation. I know both these numbers, right? So I've got sine minus 1, I've got 640 nanometers. Now a nanometer is 10 to the minus 9 of a meter, so this is 6.7, no, that's lunacy, 6.4 times 10 to the minus 7 meters, divided by 5 times 10 to the minus 6 meters. So that's really 0.64 over 5. It's equivalent to 0.64 over 5. The inverse sine of 0.64 over 5 is 7.35 degrees. And so that's the angle at which the m equals 1 bright fringe, the first bright fringe away from the center, will appear at. Okay, let me just try and 1 minute summarize. Today's class was all about diffraction. The meaning of diffraction is the bending of waves around obstacles or through apertures. Diffraction affects your eyes. Light has to go through a little aperture to get to your retina. It affects microscopes. Light has to go through microscope apertures in the microscope, affects telescopes, has to go through the lenses in the telescope. The result of diffraction in your eyes, a microscope, a telescope, is the bending of the light rays. A light passing through a small slit or small aperture will be bent outwards, diffracted outwards, and will create a larger spot, larger than the aperture, where the size depends on how small or large that aperture is. And it's a limiting effect, actually, on how well you can see because of diffraction. It's going to blur things out, and how well microscopes and telescopes can work. It limits the fact that diffraction bends the light and determines how big a spot is in a microscope or a telescope. We looked at two specific cases: single slit diffraction, where we predicted the dark fringes, multi-slit diffraction gradients, where we predicted the bright spot.